So a wave is a series of oscillations of elements which are oscillating in time. Now, it could happen that the wave starts somewhere here, and this is happening that each element which is positioned in the x direction is oscillating in the y direction. If we move a frame in time, so this is, for instance, it could be time equals 0, the blue one, while the green one could have already moved, and this is the time larger than 0. This is the motion. It's an oscillation. Is it okay? Now, as an oscillation, the largest position or lowest position that the particle can take in the y direction is going to be the amplitude. So A is going to be the amplitude. Of course, the wave has a period and it has a frequency as any given oscillation. But the distance, x distance from crest to crest, that is going to be called, which is called the wavelength. The wavelength. Now, of course, this is moving, for instance, towards the right or left. It could be moving with a velocity, and that is going to be the velocity of the wave. The differential equation or the wave equation that is modeling this phenomena is going to state that the second derivative, partial derivative, due to time, this is of position, which is with respect of x, comma, t, minus the square root of the velocity times the second derivative of this position due to the position of x, these are partial derivatives, has to be equal to 0. The solution to this kind of waves we are going to work with are going to be called the sinusoidal waves. It's not the only solution. There could be another kind of solution. But the sinusoidal waves are called the sinusoidal waves because they use the function sine. So it's amplitude sine of kx minus or plus omega t plus phi. Now, the minus or plus is due to the direction of the wave. It is going to be negative if the wave moves with a positive velocity. It's going to be positive if the wave moves with a negative velocity. Now, in this equation, k is going to be equal to the wave number, the amount of radians per meter, and this is given as 2p over lambda, while omega is, of course, the angular frequency. This angular frequency omega is as well as always given as 2p over the period, or 2p times the frequency. Phi, of course, as in the oscillation, is the phase, and the velocity of the wave is going to be equal to lambda times frequency, or omega over k. This is the relationship with the velocity of the wave.